Hi, this is John Whitaker for the Mathematical Analysis class, and this is video lecture number 3. And where we had left off last time was talking about the supremum for a set, a subset I should say, of an ordered set. And so we want to now go to an analogous definition for something called an infimum. And so here's what we have. As a definition, suppose script S is an ordered set E is a subset of script S and E is bounded below. Suppose there exists an alpha, an element of script S, that satisfies the following. So the first thing it needs to satisfy is that alpha is a lower bound of E. And 2, if alpha is less than gamma, then gamma is not a lower bound of E. Then alpha is called the greatest lower bound, of E, or called the infimum of E, which is denoted by alpha equal to the infimum of E. Okay, so as I said, this is an analogous definition to what we had for the supremum. And so the greatest lower bound, it's a lower bound, and if you give me any number bigger than it, any element bigger than it, it's not going to be a lower bound. Okay? That's what it means. And what I want to do is give an example next. So if we look at our set E equaling to -1, -0.1, -0.01, -0.001, and so forth, then this is bounded below and as a subset of the rational numbers. And it's non-empty, and so here's what we have. We have that the infimum of E is going to be equal to -1. You might remember the supremum was equal to 0 in this example. So look, the infimum happens to be in this set. It doesn't have to be in this set, but it is in this case. But the infimum may not be in this set sometimes, just like the supremum in this example was not in this set. Okay, what I want to talk about is a property that's kind of important, and it's given a definition. So here's what it says. It says, an ordered set, script S, is said to have the least upper bound property if for every subset that of S that is non-empty, and bounded below. I'm sorry, bounded above. Has a supremum in script S. So the supremum exists in the ordered set. Now, as an example, the set of natural numbers I'm going to call it script N, the book sometimes calls it J, has the least upper bound property. I'll abbreviate that LUB property. For any time that you take a non-empty subset of the natural numbers that's bounded above, then the supremum exists in the set of natural numbers. Matter of fact, the set will contain it. Subset. And that's where we define the ordering an order less than by m is less than n if n minus m is an element of the natural numbers. So that's my ordering. And m equals to n if n, or m minus n equals to 0. That's what we have. It seems kind of maybe a likely thing to think that every type of ordered set would have the least upper bound property, but it's not true. As a matter of fact, the set of rational numbers does not have the least upper bound property. And I want to prove this by looking at a few facts, okay? So here's a fact, is that there doesn't exist a p element of the rational numbers such that p squared is equal to 2. So this is a well-known fact. We want to look at it. So there's no solution to p squared equal to 2 in terms of a rational number. And so the proof is by contradiction. And suppose there existed a p element of q such that p squared equals to 2. Okay, well, since p is in q, that would mean, thus, p equals to m over n, where both of these would be integers, and n is not 0. And so I'll say, thus there exists a p equal to m over n, where m and n are integers, with n being different than 0, such that m over n squared equals to 2. And we may assume that m and n are not both even. For if they were even, we could reduce this fraction by factoring out a 2 and canceling. So we're just going to say, well, m and n is m over n is a representation of p that m and n can't both be even. As I said, because we could reduce it. We could reduce m over n. So we're looking at the reduced form. Okay. Okay, so what we have then is that m squared would have to be equal to 2n squared. We manipulate m over n to b squared equals 2. That's what we get. So this says m squared is an even number. Okay, that's because m squared is equal to 2 times some integer, so it makes m squared an even number. And thus, m has to be an even number. And this goes with the prime power decomposition of m. It's a number theoretic fact. Is that, look, for m squared to be even, that means m times m has to be equal to 2 times the number. That means 2 has to be in the prime power decomposition of m times m. That means that m has to have a 2 in it. In its prime power decomposition, we'll write down m as factors of just primes. Okay. Thus, if m is an even number, so it's got a 2 in this factorization, thus m squared is divisible by 4. So, from this fact here, that m squared is equal to 2n squared, that means that n squared, so if I divide m squared by 4, this will still have, m squared over 2, will still have a factor of 2 in its prime power decomposition. So n squared is even. Thus, n is even. And this is a contradiction because when we looked at m over n, we took the representation of m over n that not both of them were even. So that's a contradiction. Thus, what we assumed must be wrong. What we assumed is that there was a p in q such that p squared equals to 2. Thus, there does not exist a p element of the rationals such that p squared equals to 2. Okay, what I want to do next is kind of state, not kind of, state Q, this is a fact, Q does not have the least upper bound property. So here, the way we're going to do this is we're going to look at two sets. Let's define, so we'll start off with, we'll let A be the set of all positive rational numbers all positive rational numbers P such that P squared is less than 2. And then we'll define another set, let B be the set of all positive rational numbers such that let's call them P again. So the guys in B are also called P. Such that 2 is less than P squared. So we got these two sets. Now, what we're going to do next is define another rational number. So, for each positive rational number, P, define Q equal to P minus P squared minus 2 over P plus 2. So we look at this number. And this is equal to, so this can get a common denominator, this is going to be P squared plus 2P. So it's going to be 2P plus 2 over P plus 2. Okay. And if we look at Q, what we see, or can be shown, is that P is a rational number. It's a fraction of an integer over an integer, the same integer over an integer. You work with this, and you can work with that complex fraction, and you show that Q is a positive rational number. So Q is rational, as you would simplify it with this being called an m over n, integer over an integer. You get a representation of Q that isn't an integer over an integer, thus Q is rational. And it's positive because P is positive. So 2 times P is, that's a positive number. You add 2 to it, you get a positive number. You're dividing it by a positive number, so that makes a positive number. And then we're going to look at Q squared minus 2. So here, that's equal to 2P plus 2 to be squared over P plus 2 to be squared minus, and then getting a common denominator here, this will be 2 times p plus 2 to b squared over p plus 2 to b squared. And so working with this, we just happen to look at this quantity. Working with this, what we get is 4p squared plus, this is 4p doubled is 8p plus 4 minus, here this would be p squared times 2, so it's minus 2p squared. Here this would be 2p, 4p, it would be minus 8p. And then it would be 4, it would be minus 8 over p plus 2 to be squared. Okay, so simplifying that, what we get is 2b squared, so here, q squared minus 2 is equal to 2p squared, and then we have the 8p minus 8p cancels out, and then we have minus 4 over p plus 2 to b squared. Here you can factor out 2, so you get 2 times p squared minus 2 over p plus 2 to b squared. And then this reduces a little bit more. But we'll leave it in that form. Okay. Now, we start off by looking at p being the element of A. So, take something in A. What was A? A was the set of all positive rational numbers such that p squared would be less than 2. Okay. Then, p squared minus 2 is a negative number. Okay. So, that says that q, in this case, the q associated with this p, is going to be greater than p. And the reason is as q would be equal to, don't forget, it's equal to p minus p squared minus 2 over p plus 2. And so this is going to be negative, okay? And this is positive. So overall, this is a negative quantity, this fraction. And so if we subtract a negative quantity, that's a positive quantity, and p was positive, so this becomes, well, this is a negative quantity. I didn't say the right thing. This is a negative quantity, so we're taking p and, if you will, subtracting a negative quantity. That's taking p and adding a positive quantity. So that means that q had to be p plus a positive quantity. It means that q minus p is a positive quantity, thus q is greater than p. Okay, that's what we have. Okay, so since q squared minus 2 is equal to 2 times p squared minus 2 over p plus 2 to b squared, then, in this case, q squared minus 2 is negative. And so the reason that that is negative, it's pretty clear. This is a negative quantity, this is positive, and so what we end up getting is a negative divided by a positive, so that makes a negative. And so that says 2 is bigger than q squared. what that says. So Q is an element of A. Okay, again, what does it mean to be in A? To be in A, you've got to be a rational number, which Q is. You've got to be positive, which we said Q was. And then also you've got to be a rational number that's positive such that your square is less than 2. So that means Q had to be in A. Okay, so here's what we've shown. Thus, for each P in A, P is not an upper bound of A. And the reason is because we find this Q in A that's bigger than it. Okay. Now we take a look at B's, elements of B. So if P is an element of B, okay, then that means that P squared is greater than 2. So P squared minus is greater than 0. So in this case, so Q is going to be less than P. As, let's recall what Q was. Q was equal to P minus P squared minus 2 over P plus 2. And so here, P squared minus 2 is positive, P is positive, so P plus 2 is positive. This fraction is positive, so Q is P minus some positive number. That means that Q has to be less than P. So Q is less than P. I shouldn't say so. But let's look at Q squared minus 2, which equals to 2 times the quantity P squared minus 2 over P plus 2 to be squared. Okay, that quantity is greater than 0. And the reason is again, this is positive, B squared is positive times 2, well, that's greater than 0. Okay, so what we have is that Q squared is greater than 2. So this is a positive number. Q squared minus 2 is positive. Okay. Thus, Q, it's a positive number, okay, and it's bigger than, or its square is bigger than 2. So Q is an element of B. Okay, so I get to write down a similar statement to what we said about A for B. That is, so we have proven that for each P in D, P is not a lower bound of B, because I can find something in B that's smaller than P. Okay? So this shows that Q does not have the upper bound property. The least upper bound property. As A is a subset of Q, and A is bounded above. It's bounded above by everything in B. Okay? Well, I shouldn't say it's bounded above by everything in B. It's bounded above by 2. Okay. Since, and it's bounded above by B as well, okay? Since B has no smallest element, then the sup of A does not exist. Okay, so that's the proof. Really, it's any, A is bounded by any element of B. So anything that was in B was positive, and its square was bigger than 2. Okay? But if you give me if you gave me something that was an upper bound for A, well, then it was going to have to be in B, and it turns out that the B doesn't have the smallest element, so there's something less than that that would also be an upper bound for A. And so you can't get a least upper bound. So that's the proof. Okay, well, if we have a least upper bound property, we ought to have a greatest lower bound property, and we do. Let me write it up. So here's what the greatest lower bound property says. So it's a definition. It says, let script S be an ordered set such that for each subset of script S that is non-empty and bounded below then the infimum of the subset exists in script S. Then we say script S has the greatest lower bound property. Okay, it turns out that the greatest lower bound and the least upper bound properties go hand in hand with each other, and so that's a fact I'm going to write up next. As a theorem, here's what it says. It says, let script S be an ordered set with the least upper bound property let B be a subset of script S, with B being non-empty, and bounded below. Let L be the set of all lower bounds of B. Then the sup of L, which we call alpha, exists, and, or NS, and the infimum of B is what alpha is. In particular, the inf of B exists in script S. And this is essentially saying, that if you give me an ordered set script S that satisfies the least upper bound property, then it will also satisfy the greatest lower bound property. Okay, let's look at its proof. Okay, so let's put up the hypothesis. Let's let script S be an ordered set with the least upper bound property. Let D be a subset of S that is non-empty and bounded below let L be the set of all lower bounds of B. Okay. Okay, first thing we notice is note since B is bounded below, then a lower bound of B exists in S. So L consists of all the lower bounds in S of B. So that means L is non-empty. Then what we're going to do is use the fact that S has the least upper bound property. Before I go any further than that, note that for each element of B, that element is an upper bound of L. So, so L is bounded above and non-empty. Since script S has the LUV property, then alpha equal to the supremum of L exists in S. That's part of the theorem. What we want to do next is we want to show that alpha equals to the infimum of B. We have done that, but that's what we want to show. And so how do we show that alpha is equal to the infimum? Well, we have to go back to the definition of the infimum. And so first of all, alpha's got to be a lower bound of everything in B. So that's the first thing. So note, for every y element of L, y is a lower bound of B. So for each, and this is what I was saying earlier, x in B So each guy in B for each x in B, we have y is less than or equal to x, and y was in L. And that's for all y element of B. So what does that mean? That says that, so each x in B is an upper bound of L. Okay. Now, if there exists an x in B such that x is less than alpha. Remember, we're trying to show that alpha is the infimum of B. So what if there was, so the first thing we've got to do is show that alpha is less than or equal to everything in x. Okay, so what if everything in B? What if there was something in B that's smaller than alpha? Then x could not be an upper bound of L by the definition of alpha equaling to the supremum of L. So let's give ourselves a second to think about that. So let's see. Alpha is the supremum of L. That means if you give me anything smaller than it, it is not a lower bound. Okay? I'm sorry. If you give me anything smaller than it, it's not an upper bound for L, is what I should say. Okay? And so here's something, if I had it that was indeed smaller than it could be an upper bound. But it is an upper bound, so that's an impossibility. So what we get is, so alpha is less than or equal to x for all x in D. So alpha is a lower bound of B. Okay, so only one last thing to prove for alpha to be the infimum of B. So here, suppose alpha is less than some gamma, so give me something bigger than alpha. And what we have to show is that gamma is not a lower bound of B. Okay? Since alpha equals to the supremum of L, then for every y element of L, what we have is y is going to be less than or equal to alpha, which is going to be less than gamma. So, y is, so for every y element of L, what we have is y is less than gamma. So for every y element of L, y is not equal to gamma, because it's less than gamma. And by the definition of an ordering, if it's less than, it can't be equal to. And what was L? L consisted of all the lower bounds. It's the set of all lower bounds of B. So gamma is not a lower bound. So gamma is not in L. So gamma is not a lower bound of B. Thus, alpha equals to the infimum of B. And so what we have just shown is that if you have, let me write this down in our notes. Thus, this theorem, and theorem is just a big mathematical word for fact, big fact, shows or indicates that if an ordered set has the LUV property, then that ordered set has the greatest lower bound property. Let me conclude by saying this work kind of indicates that the set of rational numbers is in some sense incomplete. We'd like to be looking at an ordered set which has the least upper bound property, greatest lower bound property. And so we need, in general, the existence of a bigger set. And that's kind of the argument of why our author says, well, we need to extend this to the real numbers. We need the real numbers to get to a position where we have the least upper bound property. So we need something more than the rational numbers. Okay, that's it for this lecture. Thank you very much.